In this talk, we explore the application of generative neural networks in the context of quasi-random sampling. This research is joint work with Marius Hoffert and Mozu. The basic idea behind quasi-random numbers is to replace pseudo-random numbers with low discrepancy sequences to produce a more homogeneous coverage of the unit square. As seen from this figure, the quasi-random samples here have, on the right here, contain less gaps and clusters than the pseudo-random samples on the left. Moreover, we can visually judge that the empirical distribution of the samples on the right here appear closer to the true distribution compared to the pseudo-random samples. Now, the natural question that comes up is, how do we extend this concept to non-uniform multivariate distributions? In this talk, we will primarily view the characterization of multivariate distributions through the lens of the popular coupler framework. Copulars are distribution functions with standard uniform margins. This class theorem given here allows us to decompose any continuous multivariate distribution into its underlying coupler C, which signifies the dependent structure, and the margins fx1 to fxd. This can be visualized with a bivariate example, where a sample from a bivariate distribution is decomposed into its underlying dependent structure and the two marginal distributions. Conversely, we can also tailor any multivariate distribution by separately modeling the margins and the dependent structure. So, our goal is to generate quasi-random samples from multivariate distributions with any underlying coupler. Existing approaches are centered around parametric couplers and come in two main varieties: the conditional distribution method and the stochastic representation method. Both of these methods have limitations, making them useful and effective for only certain parametric couplers. These limitations stem from lack of numerically tractable transforms for some couplers and the difficulties in preserving the low discrepancy of the sequence upon transformation for certain other couplers. Our approach is to use generative neural networks. Now, the basic principle behind generative neural networks is as follows. Given realizations from the target distribution, we learn a neural network mapping f theta hat such that we can generate a new sample from the target distribution by simply passing a sample from the input distribution, which is typically independent uniform or an independent normal, through our trained neural network. Now, there are three key aspects to a generative neural network model setup. These are the choice of neural network architecture, the loss function used for training the neural network, and the training procedure itself. The type of neural networks we work with is known as the feed-forward neural network. The neural network can be written as a composition of L plus 1 functions, where L is the number of hidden layers in the network. And this composition yields a recursive mathematical representation seen here. All the weight matrices and bias vectors can be combined to form the parameter vector theta for the neural network. And the phi's in each layer represent a scalar valued nonlinear activation function, which is applied element-wise to the vector input. Some common functions are the ReLU activation function and the sigmoid activation function shown here. The operations of a one hidden layer neural network can be visualized as depicted here. We have P nodes to denote the input layer, D1 nodes to denote the hidden layer, and D nodes for the output layer. Since each node in a particular layer is connected to all of the nodes in the subsequent layer, we have a fully connected neural network. If you notice the operations in each node, we iterate over rows of the weight matrix and elements of the bias vector. To learn the parameters theta of the neural network, we need to choose a suitable loss function. To that end, we're interested in the question, do the samples x and y, as described here, come from the same distribution? For a given embedding phi, the MMD metric essentially measures the distance between these two sample statistics in the embedded space. For example, if phi was the identity function, the MMD metric would naturally just measure the distance between the two respective sample means. But ideally, one would like phi to be a sort of distributional embedding, in the sense that the two sample statistics contain all empirical moments of the samples x and y respectively. In practice, by using the kernel trick, we can compute this in a product with the kernel k. This yields the following equivalent expression for the MMD metric. If we choose the kernel k to be a universal kernel, such as the Gaussian kernel shown here, then the associated implicit embedding phi would indeed be a distributional embedding in the sense described in the previous slide. Then to train the generative model, our goal is to minimize the MMD distance between the training set and the neural network output by exploring the parameter space. For this exploration, we use a variant of the stochastic gradient descent known as the Adam optimizer. Moreover, we make use of mini batch optimization procedure where the batch size is a key tuning parameter, since a trade-off exists between the memory cost of evaluating the MMD versus its accuracy. Additionally, note that in practice, we use a mixture of Gaussian kernels to define the MMD loss, and we sort of standardize our data by removing marginal information and only going after the dependence. Such generative models, as we have described here, are most commonly known as generative moment matching networks, a name which refers to the key attractive feature of the MMD loss function. To generate a GMMN pseudo-random sample from the target distribution, we simply draw a sample from the input distribution and pass it through the fitted neural network. To generate a GMMN quasi-random sample, we first construct a randomized low discrepancy sequence. We then transform the sequence using quantile functions of the input distribution to obtain a quasi-random sample from the input distribution. And then we pass this quasi-random sample through the fitted neural network and obtain a GMMN quasi-random sample. The natural question that arises is, why use GMMN? There are two advantages of existing approaches for doing so. Firstly, we can generate quasi-random samples from multivariate distributions with any underlying parameter copula see compared to existing approaches with their practical limitations. Hence, this makes GMMNs an universal black box approach of sorts. Secondly, we can generate quasi-random samples from distributions with dependent structures not adequately described by parametric copulas, since GMMNs offer greater modeling flexibility. To put these ideas to practice, we trained the GMMNs on pseudo-random samples from various couples. Here are two examples of complicated bivariate mixture couplings. On the top, we have a mixture of the Clayton copula and the rotated T couple. On the bottom, we have a mixture of the Marshall-Olkin copula and the rotated T copula. In the left panel, samples from the copulas themselves. In the middle panel, we have samples, GMMN pseudo-random samples, and in the right panel, we have GMMN quasi-random samples. We see that the GMMN pseudo-random samples fairly match the samples from the true copula. Particularly in the Marshall-Olkin case, notice how the GMMN is able to capture the singular component well enough. Moreover, as you can see from the plot on the right, the low discrepancy is at least visually preserved upon transformation. It is also revealing to look at some contour plots. The solid line in each plot here represents contours of the two mixture copulas, particularly a Clayton rotated T mixture and a Gumbo rotated T mixture. The dashed lines represent contours of the respective empirical copulas of GMMN pseudo-random samples. The dotted line, the contours of the empirical copula of GMMN quasi-random samples. As you can see from both of these plots, the GMMN quasi-random samples appear to lie closer to the contours of the true copula compared to the GMMN pseudo-random samples. This again visually confirms that the GMMN samples possess some low discrepancy. Here is another visualization, but this time in 3 dimensions. On the left, we have a pair plot depicting samples from a 3-dimensional nested copula. In the middle is the GMMN pseudo-random sample, and on the right, the GMMN quasi-random sample. As you can see, the GMMN samples in the middle appear fairly similar to the true copula samples, and the quasi-random sample on the right appears to have preserved the low discrepancy, at least in these bivariate projections. To assess the quality of our GMMN-generated samples, particularly in higher dimensions, we make use of the well-known Kramer-Von-Mises statistic. This statistic, in a sense, measures the distance between a pseudo-random sample from a model and the true copula. We compute 100 realizations of the statistic based on GMMN pseudo-random samples, quasi-random samples, and pseudo-random samples from the true copula as a benchmark. Here we present box plots of these realizations for the T, for the 5-dimensional T and the 5-dimensional nested Gumbo copulas. From these plots, we see that the distribution of Kramer-Von-Mises statistics based on the GMMN pseudo-random samples and the quasi-randoms and the copular pseudo-random samples are fairly similar, indicating that the corresponding GMMNs were well trained. Moreover, we see that the distribution of the Kramer-Von-Mises statistic based on GMMN quasi-random samples lie closer to 0, further corroborating that the low discrepancy has indeed been preserved upon transformation. A primary application of quasi-random sampling is to obtain low variance Monte Carlo estimates of expectations of this form. Then if we define the composite function h and q in this manner, we have the following correspondence shown here. The first approximation here is controlled by the neural network training, and the second approximation is determined by the variance of the GMMN RQMC estimator. This RQMC estimator is constructed based on transforming the randomized QMC point set denoted by tilde VI using transform H. There are different randomization techniques that can be used. For the scrambling randomization method that we primarily work with, it can be shown using a result from Owen's paper that if all mixed partial derivatives of composite functions H exist and are continuous, then the convergence rate is given by this expression here. Many functional psi, most input distributions, and a wide variety of neural network architectures consisting of standard activation functions in each layer satisfy this fairly weak smoothness condition. Furthermore, we can show that the error between the non-randomized GMMN QMC estimator and this expectation here is bounded under certain conditions on the smoothness of H, which in turn implies a convergence rate of this order for the QMC estimator. This bound, known as the Coxma-Flacker bound, is satisfied for functional psi with bounded mixed partial derivatives for the uniform input distribution and for a fairly wide variety of neural network architectures consisting of standard activation functions. As you can see, these are indeed stronger conditions on the smoothness of the composite function H than we saw in the previous slide. An alternative randomization technique that can be used is the digital shift. For RQMC estimators constructed based on the digital shift, we obtain the convergence rate shown here if the transform H satisfies this Coxma-Flacker inequality. Here we explore the variance reduction properties of our GMMN RQMC estimators. For the quantity of interest, we look into the expected shortfall on the sum of random variables whose margins are normal. We consider phi-dimensional T and nested combo couplers. Only in the case of the T coupler can we compare our approach to the CDM-based RQMC method. All standard deviations were estimated based on 25 applications of estimating the expected shortfall. The solid line in each plot represents the MC estimator. The dashed line represents the GMMN RQMC estimators, and only in the left plot we have a dotted line representing the CDM-based coupler RQMC estimator. From these plots, we see that the GMMN RQMC estimators typically outperform the MC estimators for both couplers and has roughly similar convergence to the coupler RQMC estimator for the T. Finally, we showcase our proposed approach in the context of a financial data example. To that end, we consider portfolios of dimensions 5 and 10 consisting of S&P 500 constituents. We fit various standard parametric couplers and a generative moment-matching network to the underlying dependence structure of the S&P 500 return series. We then use a Kramer-von Mises type statistic, which essentially measures the distance between a pseudo-random sample from a fitted dependence model and the empirical coupler of the financial returns data. We compute 100 realizations of this statistic for each dependence model shown here, and for each of the two portfolios considered to obtain these two box plots. As you can see from these plots, the GMMs provide best fit in comparison to other fitted parametric coupler models, with the best parametric coupler model clearly being the unstructured T model. For the expectation of interest mu, we then use the expected shortfall for the portfolio sum. While the dependent structure was modeled by the fitted GMMN discussed in the previous slide, the margins are modeled by standardized T distributions. In the box plots, which are based on B equals 200 replications, we compare the GMMN RQMC estimators of the expected shortfall with the GMMN MC estimators of the expected shortfall. These plots clearly demonstrate that for both portfolios, we achieve a variance reduction. So, to summarize, we used GMMs to generate quasi-random samples from a wide variety of multivariate distributions. There were two main advantages of using GMMs. First was the universality of this approach compared to parametric couplers. Second was the superior flexibility of GMMs to capture complex dependent structures not well described by parametric models. Furthermore, we were able to theoretically and numerically demonstrate via simulated and real data examples the variance reduction effects achieved by GMMN RQMC estimators. All of our results uh, that we discussed in this talk are reproducible using the demos GMMN QMC paper and GMMN QMC data of a newly developed GNN RPAC. Going forward, there are two main challenges for higher dimensional quasi-random sampling. First, it is in general quite difficult to accurately learn entire distributions in high dimensions. Second, there appear to be deterioration in variance reduction effects achieved by GMMN RQMC estimators as the dimension increases. Solving these issues are open problems for future research. Here is a list of references mentioned in this talk, and thank you for listening.